Alright, in Chapter 11 we're going to learn about inference for distributions of categorical data. So this would be like tables instead of proportions or means. Particularly in 11 we're going to learn about the chi-squared goodness of fit test. This is pronounced chi-squared, not chi. Now the specific learning goals are here. Compute expected counts, conditional distributions, and conditions for chi-squared. Check random, large sample size, and independent, just like we did with random, normal, and independent. So the difference here is large sample size, and that's very much like the normal condition, and then still independent and random. Be able to perform a chi-squared goodness fit test to determine if the specific distribution meets a distribution that we believe it might meet. Examine individual components to figure out which one contributes the most to the difference, if you see a difference. Previous to this, we've discussed inference procedures for comparing proportions. We've also done inference procedures for means. The chi-squared goodness of fit test allows us to determine whether the hypothesized distribution is appropriate. I'll show you an example that will make sense at some point here. So this has to do with an activity that you can do in class called the Candy Man Can. Basically it talks about M&Ms, and what M&M's or the Mars Company claims is that it will contain 13% of brown and red candy, 14% yellow, 16% green, 20% orange, and 24% blue. So that's their claim. And what we'd like to do is open up a package of candies and see if it meets that claim. So in this chart below, what you're seeing is that there's the observed and the expected. So the observed is how many we saw. So we saw 9 blue and 8 orange and 12 green and 15 yellow and so on. What you expected based on these percentages up here. So that is, if you take the total and multiply the total by these percentages, you expect to get a little bit more than 14 blue, you expect to get about 12 orange, a little over 9 green, and so on. And based on these side-by-side box plots, you can see there are some differences. So the question is, are these different enough? The same question we've always been coming down to. Is the difference enough to say it's statistically significant, that we can reject the claim? And again, the claim is the red bars, and what we got were the purple bars. Are they far enough apart that we can reject the claim? So here, the chi-squared goodness of fit test will be able to answer that question for us. So what we're doing is we found out that there were a total of 60 candies when we added up all the ones that we got in our bag. Okay? And we found this proportion of blues. Now, you could just simply test the proportion of blues against the claim. The claim was that there be 24% will be blue. And you could do a one proportion z-test for that. But that's only going to test the blues. It won't tell us about the oranges or the greens or the yellows or so on. So what we'd like to do is we'd like to compare them all. So we're going to compare the observed and the expected counts. How many did we actually get of each candy, and how many did we expect to get of each candy? And for this we're going to use what's called the chi-squared goodness of fit test. So the null hypothesis is here in this box. And again, it's a hypothesis of no difference. The null hypothesis here, the company's stated color distribution is correct. So the distribution of 24% blue and 20% the other color, that is correct. And the alternative is just that it's not correct, that there's some difference. We don't know which one is different, but there is a difference. So in this case, we can write it with the candies this way. You can write it with all the proportions and actually write the numbers and then say at least one of them is correct. Or you can write it like you did in the last slide, saying that all the distributions are what they expected, or that one of them is not. Okay. Then we're going to compare the observed counts and the expected counts. So what we observed is right here. Okay. We observed 9 blue and 8 orange and so on and so forth. And then for our expected, that's here. What we do is we take 60 times the probability of each one. This is the claims that Mars made, and here's for blue. That one was already done. So these are all the expected numbers right down this row. And to get the chi-squared statistic, this is like the test. This is the test statistic, like the z-score or the t-score that we get when we do the other tests. We take the observed minus the expected, square it, divide it by the expected, and then sum all of those, and that will give you the chi-squared test statistic. Here's an example. So the observed was 9, the expected was 14.4, so 9 minus 14.4 squared over 14.4. So observed minus expected squared over expected. And then the reason there's 6 of these is because there are 6 columns here, 6 colors of candy. So then you sum them all. That's what this means, the summation notation right here. Okay? So this is summing them all. You get a chi-squared test statistic of 10.18. And this seems rather large because we're used to things being, 2, maybe 3 standard deviations away. And this will depend. That may be large, it may not be. It depends on a few things. That is actually somewhat large. On. Now we're going to compare it to the chi-squared distribution because we're no longer using a t-distribution and we're no longer using a normal distribution. We're doing a chi-squared test. We're going to use a chi-squared distribution. And this is what it looks like. And what you see is it's skewed to the right, so most of the data is going to be on the left. But as the degrees of freedom go up, so as you have more and more groups, it will get closer and closer to sort of a normal distribution. But it starts at 0 and it goes positive. So you'll never get negative numbers because you're squaring the difference. So that's always going to be a positive number. Now the degrees of freedom are the number of categories minus 1. So in that candy question, there are 6 categories. 6 minus 1 is 5. There were 5 degrees of freedom. So here's back to that candy problem. There's 6 minus 1, or 5 degrees of freedom. We got a chi-squared statistic of 10.18. So here's the distribution. There's 10.18, and the p-value is again the area out here. So we're wondering, how likely is it to be this far away from what we expected or further? Because we expected 0. We expected the observed and expected counts to be the same. That's why we call them the expected counts. So our chi-squared test statistic would have been 0. Now as the observed are away from that, we get a chi-squared test statistic that gets bigger and bigger. Now you can use the table. So this is them using the table, which is on the formula sheet, and looking up what that means. So with 5 degrees of freedom, a chi-squared test statistic of 10.18 would fall between 9 and 11. So that means the p-value is between 5 and 10%. So based on this, we are going to fail to reject the null hypothesis, as it says here, because the p-value is greater than 5%. You can also do a chi-squared CDF in your calculator and get the exact p-value. So this is how you carry out the goodness of fit test. Okay. That was the do. We basically have gone through the do. This will get through some of the conditions. Okay, so random as it is normal. So large sample size, here's how you verify it. It's no longer n times p. It's not the central limit theorem. It's just the expected counts are at least 5. So large sample size, all expected counts are at least 5. Independence the same. Okay. Individual observations are independent. Now, if you're doing it without replacement, okay, if you're sampling from a population, it's the 10% condition. If you're doing an experiment, it's the experiment being random. So then for us to carry out the test here, we'd state the hypotheses. So in this case, you'd say the distribution of Mars candies was equal to what the Mars company claimed, or it was different. Or you can state all the p-values. Okay. And then you find the expected counts by multiplying, as it was shown in the last slide, and you observe minus expected, and that was all shown previously. Okay. Now, be mindful that this big red explosion here, okay, the chi-squared test compares observed and expected counts. Do not do this with proportions. Okay. If the observed proportion that they give you is 20%, 24%, 15%, and so on, and then you calculate the observed proportions and compare that to the expected proportions, that's not going to work. You have to use counts. Okay. And also when you're checking large sample size, make sure to examine the expected counts, not the observed. So if you expect to get, 6 red candies and you open up a bag of candies and you only get 2, that doesn't fail the conditions because you still expected to get 6, and that meets the condition of greater than 5. So there's just another example of working through the chi-squared procedure. So well, I'm going to talk through this. It says, are births evenly distributed across the days of the week? So this is births on each of the days of the week, so Sunday, Monday, Tuesday, Wednesday, and so on and so forth. Now, we would expect these to be evenly distributed. So if we added all these up and divided by 7, we should get the expected counts for each of these. So we expect the proportion of births on each day of the week to be 1/7 of the total births. And then we're going to test to see if it's not 1/7. Okay? So there's our null hypothesis. You can also say it this way. Okay? Birthdays in a local area are evenly distributed, or birthdays are not evenly distributed. So these are the two ways to say the null. I'll usually go this way and not even worry about the numbers. Okay? We're going to use alpha as 0.05. So now we're going to do the plan. We're going to, if conditions are met, we're going to do a chi-squared goodness of fit test. The data came from a random sample, so check. Large sample size. If the null hypothesis is true, all of the expected counts here would be 140 divided by 7, or 20, because there's 140 births that they calculate up here. So 20 is greater than or equal to 5, so it meets the large sample size condition. And then independent, since there are 140, you times that by 10, there's going to be more than 1,400 births in this local area, since it's a large city. So now we're doing observed minus expected. We got 13 on Sunday, we expected 20. 23 on Monday, we expected 20. 24 on Tuesday, expected 20. And then you square that and divide by the expected counts. Here's the chi-squared components. So each of these is a component for each of the days of the week. So you can see right now that Sunday and Thursday were the ones that contributed most to the chi-squared test statistics. Those are the ones that were the weirdest. These are called the chi-squared components. So those 2 days were the ones that were furthest away from what we expected. The sum of all the components is the chi-squared test statistic. It's 7.6. So if you do a chi-squared CDF in your calculator and put in 7.6 with 6 degrees of freedom, because there were 7 days of the week, okay, and remember it's 6, there were 140 births that we looked at. The chi-squared test statistic is not 139, it is 6. It's the number of categories minus 1. You'll get a p-value that's, between 0.25, around 0.25, and it's here 0.269. Now, certainly since that p-value is greater than 0.05, we fail to reject the null, and then these births do not provide evidence to say that local births are not evenly distributed. There's another example of this one's about Punnett squares. It talks about traits that you inherit from, usually like parents, or from, maybe in this case talking about plants. Okay? So in this case they're testing the hypotheses about the distribution of offspring, okay, in 84 randomly selected pairs of yellow-green parent plants. Of the 84 offspring, 23 plants were green, 50 were yellow-green, and 11 were albino. Do these differ significantly from what the biologist had predicted? He predicted a 1 to 2 to 1 ratio. Okay? So if there's 84, we got to figure out what a 1 to 2 to 1 ratio is. So that's 1 plus 2 plus 1 is 4. If we divide this by 4, okay, you're going to get 21. So we expected 21, 42, and 21. That would give us a 1 to 2 to 1 ratio. And you're seeing that right here. 21, 42, and 21. That's what we expected. This is what we observed. Okay? So this is going through that same process again. That we expected these proportions, and we're going to see if that's just not true. And we'll state our significance level in the hypotheses. It was random. All the expected counts are greater than or equal to 5 because they're here. And then independent. Individual offspring inherit their traits independently from one another. And then this is an experiment, so they're also saying since we're sampling without replacement, because they're not putting the things back into the mix, then it meets this condition. Okay? Either of those actually would be fine. Now we're doing the do. So we calculate the test statistic, observed minus expected, squared over expected. Do that for all 3, and you get this total of 6.479. Now this one only has 2 degrees of freedom. Okay? So that's not very big. So at 2 degrees of freedom, we get a distribution that's much more, skewed to the right, with sort of this peak on the left. So if you do a chi-squared CDF, you get 0.0392, and definitely that's small. So since this is less than 0.05, we reject the null. We are convinced, or we have convincing evidence, that the hypothesized distribution is not correct. Okay. Now, they're saying to follow us up, and they're going to talk about the components. The components of the chi-squared test statistic are each of these separately. This one was 0.19, 1.5, and 4.762. So the one that contributed most was albino. We expected 21 albino, we only got 11. So we had way fewer albino than we expected. So that's the one that contributed most to the chi-squared test statistic. So this is the summary of it. Okay, so we were looking at tables that would display distributions. We used the goodness of fit test to see if the distribution that we got met the distribution that we expected to get. We compare observed and expected counts with this formula, okay? And this formula is on the formula sheet that you can use on the exam. Okay. We get a chi-squared statistic, and then we can look this up with a chi-squared CDF. The things that need to be met are we need to make sure we have a large sample size. That's kind of the new condition to you, and then random and independent. Those are the two main things. Large sample size means expected counts are at least 5. Again, it's expected counts. If the test finds a statistically significant result, you may do follow-up analysis and figure out which has the largest component and would contribute the most to the chi-squared test statistic. And then this is what we're going to be doing next. We're going to be looking at the chi-squared test for homogeneity and association or independence.